Welcome to the deep dive. Today we're looking at, well, a really fundamental piece of physics, superconductivity, and specifically how Leon Cooper in the BCS theory explained it back in '57, drawing from his Nobel Lecture.
It's a great topic because it tackles this really puzzling paradox in the experimental data.
Right, so the mission is to see how this idea of electrons pairing up microscopically solve these contradictory results.
Exactly. You start with a normal metal, right? Electrons acting independently, filling up what's called a Fermi sphere.
Yeah, just zooming around. And the Pauli principle keeps electrons with the same spin apart, but not much else correlating them.
Pretty much. You could excite electrons near the top, the Fermi level, with almost no energy cost. That was the standard picture.
But superconductors are totally different.
Completely different. The BCS breakthrough, Cooper's insight, was this weak attractive force between electrons.
Sounds weird because they repel, right?
They absolutely should repel.
But under the right conditions, mediated by the lattice vibrations, they can form pairs, Cooper pairs.
Yep.
Okay, and these aren't just any pairs, they're specific.
Yes, singlet pairs, zero total momentum. And this pairing, it fundamentally changes the energy landscape. It's not gradual.
How so?
It opens up a distinct energy gap. We call it delta L.
Ah, the famous gap.
So now you actually need a minimum chunk of energy delta just to break a pair apart and create an excitation.
And that's the key to zero resistance, the superfluid behavior.
That's the heart of it. No cheap excitations available means they flow without scatter, without resistance.
Okay, so this leads to that two-fluid idea, right? You've got the superconducting pairs, the superfluid, and then maybe some leftover normal electrons or broken pairs, the quasi-particles.
Yeah, that was the intuitive picture, like two liquids mixed together. And as you cool below the critical temperature, you'd expect the normal fluid part to just shrink away.
Makes sense. Less thermal energy, fewer broken pairs.
And so any measurement that interacts with those normal electrons should just drop off smoothly, right?
Right, and did it.
Well, sometimes. Take ultrasonic attenuation, sending sound waves through the metal.
Okay.
Morse and Bohm did experiments. Sound waves jiggle the lattice, and that jiggling mainly scatters off the normal electrons.
So below $TC.
The attenuation dropped sharply, very rapidly. It looked just like the normal fluid was disappearing, exactly as the simple two-fluid model predicted.
Okay, one for the simple model. Seems straightforward.
But then you have the nuclear spin relaxation rate.
Oh, I sense a butt coming. Hebel and Schlichter's experiments.
Exactly. This measures how quickly the nuclear spins in the material can dump their energy into the conduction electrons nearby.
So you'd expect that rate to drop too, right? If normal electrons are vanishing.
That's what everyone thought. But nope. Just below TTA, the relaxation rate actually spiked. It jumped up by more than double.
Whoa, wait. Double. It went up.
Way up, before eventually dropping off at much lower temperatures. So you have one measurement dropping sharply, another one spiking upwards at the same time in the same material.
That completely contradicts the simple two-fluid idea. How can the normal component be disappearing and somehow getting better at relaxing nuclear spins at the same time?
That was the paradox. It showed the simple picture was wrong. The paired state, the superfluid, wasn't just inert, it was doing something quantum mechanically subtle.
Okay, so this is where the full BCS theory and these coherence factors come in, to explain this weirdness.
Precisely. It's about quantum interference. The paired wave function itself affects the probability of these interactions happening.
How does that work?
It boils down to these coherence factors in the transition probability calculation. And crucially, their value depends on how the interaction, the thing doing the measuring, behaves under time reversal.
Time reversal, like running the movie backwards.
Sort of, yeah. Does the interaction care about the direction of motion or spin? For ultrasonic attenuation, the operators involved are even under time reversal. They don't really care about spin direction. And for those cases, the maths works out so the coherence factors effectively cancel the effect of this pileup of states near the energy gap. You just see the effect of fewer normal electrons.
Leading to the sharp drop. Got it.
But nuclear spin relaxation involves the electron spin flipping. That interaction is odd under time reversal.
Ah, so it does care about the direction.
Right. And in this case, the coherence factors conspire to enhance the effect of the high density of states just above the gap. They don't cancel it out, they amplify it.
And that amplification causes the spike, the peak, just below 200 colors. Wow.
Exactly. It was this detailed quantum mechanical interference effect built into the BCS paired state that resolved the paradox. It proved the pairing was real and had these specific quantum properties.
That's really elegant. And this whole idea of correlated pairs, it's not just for regular superconductors anymore, is it?
Oh, no, it's huge. This concept of fermion pairing is thought to be crucial in understanding atomic nuclei, the insides of neutron stars, maybe even liquid helium-3 at ultra-low temperatures. It's a fundamental pattern in quantum matter.
It really changes how you see these systems. Leon Cooper had that great quote about theory not just being useful, but being like designing a beautiful space, an ordering of experience.
It highlights the beauty in the mathematical structure needed to explain nature. You look at a simple piece of metal, but to understand it near absolute zero, you need this incredibly rich, complex quantum theory.
And that theory perfectly explains why two seemingly simple experiments gave completely opposite results. Quite a deep dive.